Greetings everyone. What happens when you combine heavy augmentation composition, a nonlinear projection head between representations and the loss, and very large batch sizes in contrastive learning? Well, according to researchers from Google, you get SimCLR, which argues that strong visual representations can be learned from unlabeled images using these three ingredients. We asked the question, do these design choices still matter when data and compute are limited? Our contribution was to simply rerun the ablations at small scale to test which of SimCLR's choices are structural and which are scale dependent. And we used SimCLR as our foundation.
Our work is a reproduction and controlled ablation study. We re-implemented the SimCLR from scratch and ran it on CIFAR-10 and STL-10, two standard benchmarks that fit within modest compute budgets. The CIFAR-10 gave us our primary ablation testbed at 32 by 32 resolution with 50,000 training images, while the STL-10 let us check whether our findings held at a higher resolution. Every design choice, that is augmentation, projection head, and batch size, was isolated and then tested individually.
So here's how SimCLR works and how we explored it in this current project. So we take one image, make two augmented versions of it. So both augmented versions go through the same ResNet 18 encoder with a CIFAR adapted stem, which gives us a 512 dimension representation for each of them. Then those representations go through a small projection head that maps them down to 128 dimensions and then normalizes them. So the NT-extend contrastive loss pulls the two views of the same image together in that embedding space and pushes every other image in the batch apart, and we scale this by a parameter of 0.07. So to measure the quality of the learned representations, we use standard linear evaluation protocol, which has 3 steps: pre-training the encoder with contrastive loss, then freeze it completely, then train a single linear classifier on top using labeled data. So we report the top 1 accuracy on the test set. So for us, we experimented with 200 epochs with 1 seed at the beginning, and now we are exploring to 800 epochs with 3 seeds to validate our theory. For our baseline, we got 76.36% using the CIFAR and 68.03% using the STL-10. And we expected a performance of 85 and above, but because we use less epochs, we got less than that.
From the single augmentation ablations, the headline result is that removing random crop drops accuracy by nearly 29 points, while removing flip and blur costs less than 2 points. Color, jitter, and grayscale fall in the middle. This shows us that cropping is load-bearing and everything else is secondary. From the interactions and stress test ablations, we see that color-anchored pairs stay strong. Among harmful augmentations, rotation and noise hurt significantly, but solarization, which looks aggressive, actually improves accuracy. That anomaly is what motivates our proposed contribution. The standard recipe treats augmentation composition as a universal fixed pipeline, but our results show that augmentation utility in the dataset is dependent on the dataset. Solarization helps on CIFAR-10, although it has been classified as harmful in the standard taxonomy. We propose Augmentation Saliency Scoring, a lightweight framework for dataset-aware augmentation selection. The idea is that after a short 50-epoch warm-up, compute alignment and uniformity scores for each augmentation applied in isolation. Alignment measures how close positive pairs are in the embedding space, and uniformity measures how evenly embeddings spread across the hypersphere. Together, they capture whether a given augmentation is creating views that are informative without being too easy or too destructive. We will then use those scores to rank augmentations and select the top K for full training with no exhaustive search or hand tuning.
In conclusion, here's a few takeaways. First, SimCLR does reproduce at small scale, but the gap to the paper's numbers is real and training length matters. Secondly, not all augmentation choices are equal. Cropping dominates, combinations interact in ways that aren't additive, and some intuitively harmful transforms can actually help.